in 2003, and this is the 24th distinguished lecture in the series. Today we have with us Professor TARAKANTA NAYAK from IIT Bhubaneswar. He is with Mathematics Department here in IIT Bhubaneswar. Professor TARAKANTA NAYAK received his PhD from IIT Guwahati in 2006 and did his postdoctoral research at Tsinghua University, Beijing and Harishchandra Institute. His main area of interest is the so-called complex dynamics, that is, dynamics of functions on the complex plane. That is called complex dynamics. He has 5 students registered for PhD with him. He got Ramanujan Prize in 2018 given by Ramanujan Institute of Advanced Studies, University of Chennai. And he has got about 30 publications in various international journals. So may I request Professor TARAKANTA NAYAK to speak on the Mandelbrot set. Professor, please.
Good morning to students and teachers present here. It is not only a privilege to be here, but also a very good thing for me because since long I have been very fond of this place, Kerala, because of its natural beauty, people, and most importantly, the culture of knowledge and culture represented by our country. I find it here in a very lively way. So, thank you, sir, for giving this opportunity for me to be here. Okay. So let me start. Before I start, let me say a few words about the title. So the title Mandelbrot set was not supposed to be there in this title. It is because of Sir Vinod Kumar that I put it, because he said that probably I should say something related to this. But my main focus and my expertise is on transcendental maps. So I will be spending a little bit more than half of the time on the dynamics of transcendental map, though it will be motivated by the Mandelbrot sets. So let us first see what is Mandelbrot set. Of course, Mandelbrot is name of a person who championed the idea and the research following the word fractal. So let's see what is that. Okay, so C is a complex number. We all know complex numbers, right? So complex numbers. The set of complex numbers, we call it the plane. So as mathematics connects ideas to reality, we understand that C as a plane, but C is not a plane, right? And it is not, but we understand the set of complex numbers as a plane, right? The plane that we see. Okay. So if this small c is a complex number, it is not showing on the screen, but it is showing elsewhere. So c is a complex number. What will happen to this sequence of complex numbers starting with c, 0, and then c square plus c square plus c square plus c, and so on. So there is a pattern in this sequence, right? But then what we can say about this sequence for a given complex number c? That is the starting point of Mandelbrot sets. Later we will see why this sequence and what is its connection with dynamics. So the set of all complex numbers c such that this sequence is bounded, meaning the set of all these complex numbers is inside a big circle centered at origin. For example, if I take c equal to 0, what I will have? 0, 0, 0, 0. So this is a bounded sequence. So the point 0 will be in this set. It will be somewhere here. Yeah. So yes, the natural question about the sequence is convergence, whether it converges or not. If it doesn't converge, then whether it can have a convergent subsequence. So we will understand convergent sequence. Matrix. So convergence means you have a sequence of numbers, then you say it converges to something. If near that something, all the members of this set are there except finitely many. That is the usual understanding of convergence. For example, your favorite sequence 1, 1 by 2, 1 by 3, 1 by 4. So this converges to 0 because around 0, if you take any interval, you will find all the members of this set except first few. That is convergence. So, but here we are not talking about convergence of this sequence, but its boundedness. We don't mind whether it converges or not. We just want when this sequence is bounded. If this sequence is bounded for some c, we'll keep that c. Then we will look at other possible values of c and look at this sequence. If it is bounded, we will keep that c also. Then set of all those c's is nothing but the set shown in black. This is the Mandelbrot set. This is the Mandelbrot set. So everything here, even here, and at these antennas here, all these things are there. It is found to be very complicated one, even mathematically, we'll see. Okay, so this set is called the Mandelbrot set. Set of all the small seeds in the complex plane for which this sequence is bounded. This is the set. This is our starting point. So it's so simple, right, to define it. But to understand this, people have taken decades and still there are certain things no one knows about this set. Okay, so why this set and hence this sequence SC is important. This is because of the following. You start with a quadratic polynomial in a complex variable z, polynomial with degree 2. And yes, I am taking the coefficient to be 1 here, coefficient of z square, and coefficient of z to be 0. Z square c is not the only quadratic polynomial, right? But it is a kind of very simple quadratic polynomial. And we say a point to be a critical point of a polynomial if the point is the one where the derivative vanishes. So derivative of this is 2z. 2z is 0 only when z is equal to 0. So that 0 is called a critical point. And it is the only one. You take any other point different from 0, derivative of this polynomial doesn't vanish, right? And this set we call the forward orbit. Forward orbit, when time changes, or in other words, when you apply this polynomial PC on 0 again and again, you get a set that we call forward orbit. So PC00 will be 0, PC10 will be PC of 0, that is C, PC20 will be PC of C, that is C square plus C, the third element in SC. And then, and so on. So that sequence SC is nothing but this set, the forward orbit of 0 under this map. Is that fine? So the Mandelbrot set is the set of all seeds for which this set is bounded. Just restating the definition. Okay, now let us see what are the points in the Mandelbrot set. If I take C equal to 0, then forward orbit of 0 here, it will be, of course, first element will be 0 anyway. The second element C will be 1. The third element C square plus C will be 2. Next element 2 square plus 1, that is 5 and so on. So this is the sequence SC when C is equal to 1. And at least to this sixth term, we can convince ourselves that this just go on increasing and this goes to infinity. So this C is equal to 1 is not in the Mandelbrot set because it's not bounded, it's just going on increasing. But if I take C equal to 0, then every member of the sequence is just 0, so it's bounded. So the point 0 is in the Mandelbrot set. Here, if I take C equal to I, then the first element will be 0, of course. Then the second element will be C, that is I. Then C square plus C, I square plus I, that is minus 1 plus I, and so on. And here we see that I, then minus 1 plus I, and the next member will be minus y minus 1 plus I square plus I. That is minus I. Yeah? It's calculation, right? So minus 1 plus I square plus I. That is minus 1 square plus I square minus 2I plus I. Right? This cancels, this is minus I. Minus I is here. Next element. Then minus I square plus I, that is minus 1 plus I. That is here. And then what will be the next element? Minus I only. And the next element will be minus 1 plus I. So, though this sequence does not converge, it is bounded. It remains 0, I, minus 1 plus I, minus I, then this element again, then minus I again, and deleted. So the point c equal to I is in the Mandelbrot set. Okay. So the picture that we saw is set of all such C's. One can write a simple program. Programs are available and see what are the complex numbers C so that SC is bounded. This will be found. This image will be found as the set of all such C's. Note that this point will be 1 by 4. Origin will be somewhere here. Yeah? And this will be minus 1 by 4, this point. And minus 1 will be somewhere here. So basically your axis will be like this. X-axis, Y-axis. So now the equivalent definition of Mandelbrot set is set of all C for which the forward orbit of 0 under the map PC is bounded. Okay. So now what does it say actually? Is it just some Mandelbrot came and created a set and gave us? Must not be that, right? There must be some important and significant background. So what is the background? You take a quadratic polynomial P, any polynomial, say maybe, yes. We can see that it is conjugate to z square plus c. What is conjugacy? So C hat is C union infinity. Then conjugacy means the following. You take any quadratic polynomial, for example, this here. So this polynomial maps C hat to C hat. It takes infinity to infinity. If you put infinity here, you get infinity, and if you take a finite complex number here, you will get a finite complex number. So this P maps C hat to C hat. So what I mean by saying it is conjugate is the following. There is a map phi of the form AZ plus B, we call it affine map or first order polynomial, so that phi inverse P phi, this map, starting from here, going back here, then here, and back. So this map will be a map of this form z square plus c. This is a small exercise. In fact, what you can do, you take any polynomial of this form, quadratic, yes. Let me take capital A. Then you just start with a general linear polynomial to solve it. What you will get? This is phi p, and phi inverse will be z minus b by a. Right? So you take, you compose these two maps, you will see that the composition is identity. So this map is inverse of this and vice versa. So if you put this in place of a p, that will be a z minus b by a square plus b z minus b by a plus c. So, sorry. No, not this. This will be phi inverse, right? Oh, this is phi inverse. So phi of yes. So the square a plus b z minus b by a plus c. Then again you apply phi small a into whole of this plus small b. Then you will find something z square plus something z plus something. Then we want this to be of this form z square plus c. So if this is to become z square plus c, then this coefficient should be 1, this coefficient should be 0. Then you will find an equation in terms of small a and small b. So you can make a choice of small a, small b. So it is possible to find a c such that this function is conjugate to any given arbitrary quadratic polynomial, for example this. That is the reason why Mandelbrot took only polynomials of this form, because if you look at the iteration of a p, that means n times composition, repeated application of a p, then from here we see that this map is nothing but PCNZ. So the iterative behavior of PC and P are same. It's a kind of normalization. If you don't follow it completely, that is also fine. So basically, it is the same philosophy which we do frequently in mathematics. We simplify certain thing without losing anything important. We call it without loss of generality. So this is without loss of generality. So if we take this quadratic polynomial, then for this 0 is the critical point, and okay, this is done. So any quadratic polynomial is similar as long as our discussion is concerned to a polynomial of this form, and the field in Julia set of this polynomial is the set of all complex numbers whose forward orbit is bounded. So it is slightly different than the definition of Mandelbrot. So here we are fixing a polynomial, fixing a C, and we are looking at all those complex numbers whose forward orbit is bounded. For example, if I fix C equal to 0, then my map is Z square. So what will be KPC? It will be the set of all complex numbers whose square, 4th power, 8th power, and all these things are bounded. What are those points? So if my polynomial is z square, so what is k z square by this definition? It is set of all complex numbers whose forward orbit is bounded. So you will see that if you take the point 0, its forward orbit just itself 0, 0, 0 is bounded. So 0 will be in KPC, kz square, and if I take half its square, square of its square, everything, its square will be 1 by 4, then square of 1 by 4 is still something near to 0. So this point half will be in the 15 Julia set. In fact, any point inside the unit circle, if you just go on squaring it, the set of all resulting complex numbers remain in the unit's disk. We will have modulus less than 1. So this will be unit disk, closed unit disk. So the field in Julia set of Z square is just this set. Yeah. And the Julia set of PC is the boundary of this set. So what is boundary of this set? It is just unit circle. So unit circle is the Julia set of Z square. By definition, we call it Julia set. Boundary means it is set of points, so that if you take any a small neighborhood of it, you will have a point which is not in the set and a point which is in the set. in the set means whose forward orbit is bounded, but forward orbit of this is not bounded. If you have a complex number with modulus bigger than 1, you go on squaring it. What will be its square? Its square will be something here. Right? Argument will be doubled and modulus will be squared. Since initial modulus is bigger than 1, square of the modulus will still be bigger. And the image of this will be something here. Image of this will be something here. So it will like rotate around the origin and at the same time will go to infinity. So the Julia set of Z square is unit circle, and it is known, it can be proved that Julia set of any quadratic polynomial is a bounded set, it's a closed set, and a perfect set. Perfect means you take any point of it, for example, unit circle. Perfect means this is a limit point of this set, meaning any neighborhood you take, there you will find another point of the same set. It's not isolated, it's not a set like this. If one point is there, you will find many points there. Perfect set. And this result, again, I will not prove it. Julia set of a PC is connected if and only if forward orbit of its critical point is bounded. So, in other words, Mandelbrot set is set of all those parameters we say C, so that the corresponding quadratic polynomial will have a connected Julia set. That's it. This is again another definition of Mandelbrot set. So, if you take C to be minus 0.75, this white region will be the filled in Julia set. And the Julia set will be the boundary of this black and white region. If you take C to be 0.01i, then the Julia set will be kind of dots. They are separated from each other. Yeah. And if you take C equal to 0.25, then the filled in Julia set will be everything except the black region, and the Julia set will be the boundary of this black region and this other colored one. And if you take C equal to I, one can see that this is like the Julia set as well as the filled in Julia set is a picture like this. It is called dendrite. So these are some possibilities of Julia set and filled in Julia set of quadratic polynomials. Okay, then the question is, if I do not take quadratic polynomial but a polynomial of say degree 3, what will be its Julia set? Whether it will be the boundary of a filled in Julia set? The answer is yes. And not only for cubic polynomial, for polynomial of any degree. You just look at all the points whose forward orbit goes to infinity. Then the rest of the points will be precisely those whose forward orbit is bounded. Then filled in Julia set, then is bounded. But if you take a map of this form, say map of this form, say 1 by z square plus 1. What will be the Julia set? How we can make sense of it? So then a general notion comes in. It is not that you just look at points whose forward orbit goes to infinity, but some other general theory comes in. So this is the standard and general definition of Julia sets, of which ours is a special case. So what is the standard definition? You take a rational map, your quadratic polynomials are rational maps, where you have z square plus c here and divided by nothing, so nothing is just 1. If you take any rational map or a transcendental meromorphic map, what is transcendental? It is a map which is analytic or differentiable at all the points of the complex plane, except at a set of points uh, like isolated set of points. So the examples are say this is the example. So this is differentiable everywhere except at plus minus I, right? This is called a rational map. So transcendental maps like Ez, this is differentiable everywhere except at infinity. Right? So say tan z, this is differentiable everywhere except at points where cos z is 0. Right? So those points are just points on the real line, they are set of isolated points that are transcendental map. And then uh, the subject dynamics is concerned with looking at all the points whose forward orbits, irrespective of being bounded or unbounded, behave in the same way when the point is changed. In other words, I take a point z, I look at z, comma, fz, comma, f of fz and so on. This is the forward orbit. Then, is it possible that if I take a point near z plus epsilon in the plane of force, so I take a point z, then I look at the forward orbit of z, then is it possible or is it true for some point of some function, note that forward orbit is with respect to a given function. Then is it possible that if I take another point nearby, of course I will get another forward orbit. So this forward orbit and this forward orbit, up to what extent their behavior is same. For example, if this is converging to something, whether this will converge to something or not. If you look at the z square example, you take 0, the forward orbit is just 0, 0, 0, 0, it converges to 0. And if you take half, the forward orbit is different but it converges to 0. That is the similarity I am talking about. So set of all the points whose forward orbit under small perturbation, under small change, some way behave in a similar way, set of all those points are called Pareto set, and Julia set is its complement. I skip this notion of normality, but it is essentially the same thing. Okay, doesn't matter if you don't understand these definitions completely. So what is this picture? If I take this map, pi plus 0.99 I plus z plus tan z, this yellow region and green region, both their union constitute the Pareto set, and their boundary, which is looking very wild, is the Julia set. Okay, now if I take any such function, what can be the possibilities of the forward orbits of all the points? So U is a periodic Pareto component. So Pareto set is an open set by definition. So if it is an open subset of the plane or the sphere C hat, then we know as student of mathematics that any open sets can be written as components. Say this is an open set, so this is one component, this is another component. So component is basically a maximally the biggest connected open subset of a set. So if set is union of these two things, then this is a component, this is a component. So Pareto set is open by definition, and a component of it is called a Pareto component. Then people wanted to know What will happen if I apply the map on the factor components, not on a point? Earlier we were interested in the forward orbit of a point. Now we are interested in forward orbit of a set consisting of many points. Because simply we cannot look at all possible points in C hat and see their forward orbit. It's just not possible. So this is a subset of the plane. It is periodic when its image is something, its image is something. But if it so happens that after some time its image becomes something that we have started with, it's called a periodic factor component. Periodic, things repeat, right? So if you have a periodic factor component, so here it is of a period 3, so that composition of F3 keeps this set intact. You call it invariant. Then what can happen to a forward orbit of these points? There are only 5 possibilities. One is that if this is a p-periodic factor component, that means if p takes this set to itself, then one possibility is that you take any point z here, then you look at f(p)z, f(2)p)z, f(3)p)z, you iterate f(p). Then all these forward orbits will go to a single point. This is one possibility. This thing we call attracting domain. It attracts all the forward orbits under FP, pth composition of A, comes to a single point contained in the set. If this happens, we say this kind of factor component to the attracting domain. And if the same thing happens, but the point is not inside the set, in our language we call it interior point, but on the boundary, then we call that domain as a parabolic domain. It also kind of attracting, but the point of attraction is not inside the set, but on its boundary. Then another possibility is that for a p-periodic factor component, you take a point, it does not get attracted to anything, but it remains on a circle. Say a point here, its image will be here, then its image will be here, then image will be here. So the forward orbit will remain on that curve, but it will not get attracted to anything. This can also happen. If this happens, and if the component is kind of with a hole, we call it doubly connected. This complement has two components. Then we call it Harmony. If the same thing happens for a domain without a hole, for a simply connected domain, we call it serial list. This Harman and serial are the persons who are the first to discover that these are the possibilities for some function. By their name, the domains are named. And the other possibility is that you have a domain, your points get attracted to a point on the boundary, but the point on the boundary is a point where your function is not defined. For example, if you take Ez, it is not defined at infinity. It's called essential singularity. It's not defined there. So if this attracting point is on the boundary, but unlike parabolic domain, the point is such that function is not defined there. So when I say it is not defined, it is not possible to define the function at that point so that it's continuous there. Right? So these domains are called Baker domains. And these are the only 5 possibilities of factor components for any function you take. Any rational function of any degree you take. Any transcendental map of any type you take. These are the only 5 possibilities. So this makes things easier. Of course, the proof that these are the only possibilities is very technical. You need to know many things to really understand why it is so. Okay. So, just like critical points, the points where the polynomial was vanishing was very crucial in determining whether its Julia set is connected or not. Recall the definition of Mandelbrot set. For transcendental maps, there are some points A to which the function tends when z tends to infinity along a chord. So, when the function is having a transcendental singularity at infinity, it is not defined there. In particular, it is not continuous there, but it can so happen that restricted limits, restricted in the sense that along a chord. So, when z tends to infinity, it can tend to infinity in many different ways. If it so happens that there is a chord gamma, unbounded chord, and when your z tends to infinity along this gamma, then function tends to something that's called asymptotic value. The simplest example is this. When your gamma t is minus t, t between 0 to infinity, when t tends to infinity, gamma t tends to minus infinity, right? Along negative real axis. And we know the graph of Ez is nothing but this. Ex. Ez restricted to real line. So when z tends to infinity along negative real axis, Ez tends to 0. 0 is an asymptotic value. Is the simple example. And we look at all the points where derivative vanishes and all the points like this. Take their union, take their closure, because this set can be an infinite set. It can be very wide. Even this set can be spread throughout the plane. Many possibilities are there. So we take the closure, means those set and the points to which they tend, the set of the limit points. We call it singular value set. And then what you do, we look at the forward orbit of the singular values and take the union and then closure. So basically, it is the singular values whose forward orbit tell us what will happen to forward orbit of other points. That is why the question of understanding forward orbits of points under a given function, which is the primary concern of complex dynamics, reduces to looking at forward orbits of singular values, because singular values are usually very few. Like for Ez, the set of singular values is just 0 and infinity. So if you know what happens to the forward orbit of 0, that means 0, 1, e to the power e to the power e to the power e. This is the forward orbit of 0, right? If you know what happens to this, you can know what happens to any point under iteration of Ez. That's why people say that singular values determine the dynamics. They tell us what is going to happen to other forward orbits. Of course, I mean, this statement is not mathematically true, but mostly can be done. Because there are some points whose forward orbit can never be known, but set of those points actually is a subset of Julia sets. Except that, we can know. Okay. So now the quadratic polynomials are the simplest maps because they have a single critical point whose forward orbit we should be concerned with to know its dynamics. But then if I take a high degree polynomial, say polynomial of degree 10, it will have many critical points. Then you have to many but finitely many. So the situation is a bit difficult, but theory have been developed and we know many things in general for the forward orbits of any point under any polynomial. You know. And then comes maps like 1 by z square plus 1, rational maps, it is still complicated. And here only these Hermann rings that we show, they can arise. Hermann rings cannot be possible in this case. Then comes transcendental maps like EZ, TANZ, SIN Z, etc. And then comes transcendental maps whose singular velocity is bounded. This is the famous Eremenko-Lubitz class. So famous, if I am permitted to tell non-mathematically, this class is famous because some information about maps of this class recently means maybe 5 or 6 years or 10 years ago, appeared in the best mathematical journal of the world called Annals of Mathematics. That is one reason I can say why this class is famous. I repeat, this class of maps is famous because some knowledge about maps in this class appeared few years ago in the topmost journal of the world. And what I am going to talk about is about a map which is not in the class. It is this map. So you can say, what is great about this map? Anyone can say, right? So it is just like what was great about the quadratic polynomials. I'll justify why this map, because this appears as Newton map for some tangential map. Recently, this appeared as a map disproving a conjecture of a few debtors by I.M. Baker. So there are justifications. I will not go into the details. So this is the map we are considering. We can see that this has infinitely many poles. Poles means the points where the limit is infinity and all of them are real. It has no finite asymptotic value. In other words, you take any curve going to infinity, you take the limit of this function, you are not going to get a finite limit. And there are infinitely many points where its derivative vanishes. They are precisely this constant. So what is this point? This real part is pi by 2 plus pi k, k is an integer, and imaginary part is same. So basically, the critical points are on the upper half plane on the same straight line, horizontal line on the x-axis, and its reflection along x-axis below in the lower half plane. You have another set of critical points. These are some informations about the map, and if you take lambda is equal to plus or minus I, it has no fixed points. You cannot have a solution of if you take this equal to z cancels. So if lambda is plus minus I, then tan z equal to minus plus I has no solution because tan z cannot take the value I. So you don't have a fixed point, but if you take other lambda, there are fixed points. In fact, infinitely. What are fixed points? They are the points whose image are themselves. They are also very important from this perspective of dynamics. And another good thing about this map is that their multipliers are same. What is multiplier? Okay, attracting, repelling, indifference. So what are these notions? We call a fixed point or a point which is its own image attracting when problem happens. So again, look at this easy map. 0 is fixed point, right? 0's image is 0. And P0 z. And P0 prime z is nothing but 2z. So P0 0 is equal to 0. Its modulus is less than 1. So 0 is an attracting fixed point. Point of z square. Similarly, we can have other functions like this. 0 is also a fixed point here, right? But its multiplier is not 0 because its derivative is 1 plus 2z. So multiplier means derivative of the fixed point is actually 1. So the modulus of this multiplier is 1. So when modulus of the multiplier is 1, we call it indifference. When modulus of the multiplier is less than 1, we call it attractive. When modulus of multiplier is bigger than 1, it is called repelling. Repel. What does that mean? That means the following. If you are an attracting fixed point, then there is an open set where if you start with a point and look at its forward orbit, it will come near this point, it attracts. If it's repelling, it repels. You start with a point nearby, its image will be away from the fixed point. Indifferent, there are some different possibilities of things. So here, what happens, all the fixed points of this function, altogether everyone is attracting or everyone is repelling or everyone is indifferent. This is not a very general thing about functions. Because for a function you can have some fixed points attracting, some repelling, some indifferent. Anyway, so we are basically interested in the value of lambda. Let me repeat. We are interested in the values of lambda for which this is having a connected Julia set. This is where it connects with Mandelbrot set. But since the Julia set and factor set of this function is having a more general definition than quadratic Julia set, so some work needs to be done. Extra work. Here, one important observation is that if you take f lambda and f minus lambda, dynamically they are same. Like this conjugacy, we can construct a Mobius map via which we can go from dynamics of this to here and vice versa. So it is enough to consider those parameters lambda with positive imaginary parts. And it is observed that if parameter is having positive imaginary parts, and this should be z answer. And if you take a point in the upper half plane, meaning with imaginary part positive, then image of it will also have imaginary part positive. In other words, the upper half plane contains its own image under f lambda, when imaginary part of the parameter lambda is positive. So that, using some known thing, says that the upper half plane is contained in a Pareto component. And with a little effort, we can find that that is a Becker domain and it is CIFC. CIFC means completely invariant Pareto component. That means its image is contained in itself and its full pre-image is also contained in itself. Again, coming back to this example of z square, note that image of unity disk is itself, and the full pre-image, meaning the set of all points which are coming to unit disk, are nothing but the points in the unit disk. You cannot have a point outside this which will come inside this under the axiom of map. So unit disk is completely invariant. Forward invariant, backward invariant. Like that. That will be a set containing H plus upper half plane, which under the map F lambda is forward invariant, also backward invariant. That is actually Pareto component, and that's a Becker domain. So we call it a primary Pareto component. Observe that for Z square plus C, it was always a set here. So this black region actually is the set of points which goes to infinity under iteration. So this is a Pareto component. This is the primary Pareto component. But yes, this is also a Pareto component, white region. And here, the only Pareto component is the black region, because these white regions are actually not open sets. They are just dust kind of thing, set of points, like Cantor sets. So like this, in that example, we have this yellow region, for example. This is a member of this family for lambda equal to pi plus 0.99i, and this yellow region is that vector domain. Now, if I take lambda such that this equation is true, what is the set of such lambdas? These are some open sets around plus minus root over 2i. So if I take such lambda, we will see that there are infinitely many such things. They are actually attracting domains. This red thing is the primary factor component vector domain, and here you will have a point to which every point in this blue region will converge under iteration. So this is an attracting domain for some parameter, and for some other parameter this domain tilts a little bit. But for every lambda you will have infinitely many attracting domains invariant. Invariant means its image is itself. So its period is 1. And they are such that this is some extra information that the imaginary part of the points in this attracting domains is unbounded. They are unbounded below, but the real part is bounded. They can be realized within some vertical strip for these lambdas. And for lambdas whose imaginary part is between 0 and 1, basically when the parameters are on a horizontal strip above the real axis with width 1, then the factor set contains another vector domain V tilde different from the primary factor component, which is always there for any lambda. And when your imaginary part of the parameter is bigger than this number, then we don't have any other factor component other than the primary one, and Julia set is not connected. Whereas in this case, not for all lambda, but you see, but for those parameters whose real part is k pi. Anyway, I have the picture of the parameter plane. Then the Julia set is connected. So, and there are some wandering domains. Let me not go into that. So, wandering domains are that those components of the factor component which never comes back to itself. Its image is something else. Its image is something else, and go on. This can also happen for these functions, which is not possible for polynomials or rational maths. So, these are some pictures of wandering domains for this parameter. Basically, this domain, its image is this, its image is this, and so on. So, it never comes back to itself. Okay. Let me just explain the picture. So, this is the set of lambdas. If your lambdas are in this, anyway, okay. So if this is origin, so if your lambda is in the upper half plane anywhere, you have your primary factor component. We don't describe that. But if your lambda is in this yellow strip, okay, what you have, okay, let me first tell you about this. So this we call attracting lobe. If your lambda is here, then you will have that infinitely many attracting domains. If your lambda is here, along with the primary factor component, there will be another vector domain. And if your lambda is here, Julia set will be disconnected. And if your lambdas will be here, the factor set will consist of some wandering domains. So this is a schematic picture, but computationally, this is the picture. So if your lambda is in this attracting lobe, you have attracting domains, and Julia set is connected. And here, computationally, not theoretically, if your parameter is there, then you have connected Julia set. If your lambda is here, you have disconnected Julia set. So, if I want to draw parallels between this situation and Mandelbrot set, I can say here the Mandelbrot set consists of this and this. I mean, it's not a very The two situations are not compatible. Yes, that is true. But still, we observe computationally that some structure like Mandelbrot set appears here. And what is the region? The complete region we do not know, but a good guess will be that the critical points of the maps that we are considering, they are the points around which the map is 2 to 1, like the map z square plus c is 2 to 1 around 0. So what is this 2 to 1? 2 to 1 is, okay, let's take this function again. If you take 0, its image is 0. But it is possible that you find two sets here, so that any point here will have two images exactly. This is how z square maps around origin. This is what I mean by saying 2 to 1. So this may be a possible reason why in the parameter plane of this very different function we see Mandelbrot's or copies of Mandelbrot's. Okay, this slide justifies why tangent. No, it may not be tangent, but you take any periodic meromorphic function whose derivative plus 1 is a function of that function itself, gh. So in particular, you take if you take h to be tan z, 1 plus tan prime z, that is sec square z, is equal to um, uh, 1. So, so this is basically a generalization of tan z. You take any h whose derivative satisfies this formula. So derivative of this function plus 1 is a function of x. So what is this situation in our case? So in our case, hz was tan z. Sorry, hz was tan z. Yes, tan z. Its derivative is sec square z. So 1 plus sec square z. So sec square minus tan square equal to 1. Okay. So this is 1 plus tan square z, correct? And this is g of tan z, where this gz is equal to 2 plus z square. Okay. So this g can be any function, and this h can be any function which is meromorphic and periodic. Periodicity is required. Then this function f lambda z, which is lambda plus z plus hz, this will have the same dynamical behavior as ours. So the choice of tan z is just convenience without loss of much generality, because whatever we have done for this function can be done for this function, and the parameter planes can be stored. So I think I'll stop here. These are some papers containing the basics. This book, very beautiful book by Jordan, describes the dynamics of decimal maps. This book, beautiful book by Milner, who is also the reputed and a field medalist, wrote this paper which deals with the transcendental situation also. And these two papers are some recent, and not recent, but they are kind of they condense general notions involving transcendental maps. And this is the paper from which most of the last part of the talk have been taken. Okay. That's all. Thank you. I would like to respond to some of the queries if you have. Because I skipped many things, I understand. If you like, I can explain them. Okay. Do you have any questions?
Free to ask questions.
Yes. You have something to ask? No, having something to ask is a good thing, right? Yeah, I understand that I did not present the things in a way that everything can be understood, because it's not possible. But at least if you get some idea and you have something more to ask about that, it's fine. It should be no question is silly, right? At least in this subject. So
How many of you have heard about the Manipur set?
this is Pradarsan.
You have to refer. This is an interesting set. There are many computer programs available to generate Manipur set or Manipur like sets. You can refer in the papers or you can go through Google.
So if you Google Mandelbrot set, at least few crores entries will come. That says how popular this set is. How many is there? 1, 2, 3. So 39 lakh 50,000 entries in Google. So it has gone much beyond mathematics. It has caught the attention of many people beyond this subject. You can even put your opinion, if not question or suggestions. This is Carlos. Okay.
Let me thank Professor TARAKANTA NAYAK for his nice presentation. It was very interesting. The topic is interesting. You may refer later if you want to know more about the Manipur set and learn things. As a token of our appreciation and gratitude, may I request our principal, Professor P.S. Rajit, to present a memento to Professor TARAKANTA NAYAK. Thank you. The session is over.